Hello everyone. Today let's solve the problem Igor and mountain. Right. So this was asked done Codeforces round 1013 div 3. Right. So this was asked done basically division 3 around 1013. Right. So here you can just go through the question. It's easy to understand basically. I'll just summarize the question so that it will be easier for us to understand the approach as well as the complexities, and then let's write the code. Right. So it will be easier for us to understand the logic and then write the code. So let me summarize the question and then let's discuss the approach and further things, right? So what the question states here, Igor climbs a vertical mountain, right? So just give me a second here, 1 second. Yeah, just give me a second. Yeah, Igor, this one claims a vertical mountain wall that is divided into n rows and m columns. So what does Igor do here? Igor claims a vertical mountain. Igor claims a vertical mountain wall that is divided into m rows and n columns. That is divided into m rows and n columns, right? Igor climbs a vertical mountain wall that is divided into n rows and m columns. Some cells have holds x. Some cells have holds x. Just remember this one, right? You'll get to know one by one. So just whatever I am reading out loud, or whatever I'm trying to say, just this one, just remember these things, right? So here Igor claims a vertical mountain wall that is divided into m this one n rows, sorry, this is n rows and m columns. N rows and m columns. Some cells have holds x. He must start at the bottom row and end at the top row. Start at the bottom row, right? He must start, Igor must start at the bottom row and end at the top row. He must start at the bottom row and end at the top row. Visit one or two holds per row. Visit one or two holds per row. Only one or two per row. One or two holds per row. Just remember this one. This is very important. That clearly given in the question that he must start at the bottom row and end at the top row. Visit one or two holds per row, and each next hold must be above or on the same level. And each next hold must be above or on the same level. So this is very important. Next hold must be above or on the same level. So he can only move between two holds if their Euclidean distance is less than or equal to d. Again, so here we have to go with the Euclidean formula. You would have already guessed that to calculate the distance, we'll be going with the Euclidean formula for this particular question. They have clearly mentioned here. He can only move between two holds if their Euclidean distance is less than or equal to d. Again, I'm telling he can only move between two holds if their Euclidean distance is less than or equal to d. So this is very important. Again, so he must start at the bottom row, this one, and end at the top row. Visit one or two holds per row, and each next hold must be above or on the same level. He can only move between two holds if their Euclidean distance is less than or equal to d. This part I am reading. This part I'm reading out loud, right? He can only move out between two holds if their Euclidean distance is less than or equal to d. We must count distinct valid routes from bottom to top. So bottom, he is starting at the bottom row. He can claim the vertical mountain wall. He has to claim the vertical this one mountain wall that is divided into n rows and m columns. He can start at the bottom row and he ends at the top row, right? He starts at the bottom row and ends at the it starts at the bottom row and ends at the top row, right? We must count the distinct valid routes that Igor can climb from bottom row to top row. Valid routes, distinct valid routes, not same valid routes. We have to count the distinct valid routes from bottom to top, satisfying the constraints, right? Again, I'm telling we must count the number of distinct valid routes from bottom to top, not the same. Again, so just keep this in mind. We must count distinct valid routes from bottom row, this one, to top. Bottom row, so this one first, he has to start with bottom, right? Bottom to top, here, this one, top row. We must count distinct valid routes from bottom to top, satisfying the constraints. Two routes are different if holds used on their order differ. Two routes are different if holds used or their order differ. Again, I'm telling the last sentence, two routes are different if holds used, if already holds used, right? Two routes are different if holds used or their order differ, right? So these things we have to keep in mind, man. These things we have to keep in mind at any cost, right? So I hope this part is completely clear, right? The question part is completely clear. We need to count the distinct valid routes now from bottom to top, satisfying all the conditions whatever we have discussed, right? Whatever we have discussed, and we will be making use of the Euclidean formula, or the Euclidean distance has to be less than or equal to d. Means he can only move between the two holes if their Euclidean distance is less than or equal to d. They have strictly mentioned in the question. Euclidean distance has to be less than or equal to d. They have strictly mentioned in the question. Just keep this in mind. As well as he has to move from bottom row to top row, and we have to count the number of valid routes from this one. Routes from bottom to top, not routes. Sorry, yeah, routes from bottom to top satisfying the constraints, right? So two routes are different if holds used or their order differ. So I hope the question part is completely clear now. A bit tricky, a bit tricky question, but I hope the question part is completely clear. So easy to understand if you break the question into pieces, right? So if you break down the question and then try to understand, it will be easier to understand. So we will be going in the same way that uh, we studied the question step by step, right? So we'll be doing the same thing with the approach as well. We'll break down the approach into several steps, and then we will see step by step whether how many valid routes are there for the particular input, how many valid distinct routes that the Igor can use to this one climb from bottom to top, satisfying the constraint. So here we have three inputs. They have given three total. First three is nothing but the total. We have three inputs, this one and this one. For the first one, 3 4 1, we have to get the output 2, right? So there are two valid routes for the first one, two distinct valid routes. For the second one, we have 60 valid routes. So this one, if I consider, I might not able to this one explain 60, right? So I'll just consider the first input, right? So for the third one, we have 0. So this will also, if I consider this one, this will also be waste. We don't have any valid route. So for the valid, you will not understand at all. So let's do one thing. Let's consider this one, this input, right? So we have to get the output 2. So we have to get the output 2 in this case. So this is nothing but 3 4 1 whatever they have given. So just give me a second here. So let me explain the input correctly. This is this 3 whatever they have given. This is n, and this is nothing but the m. N is nothing but the number of rows. This one, n is nothing but the rows, m is nothing but the column, and 1 is nothing but this one, d, distance. D nothing but the distance. So number of rows is 3. Here you can clearly see number of rows we have for the first input is 3. Double x hash x hash double x hash hash x hash x. So these are the three rows we have here. 1 2 3, and 4 is nothing but the number of columns. Number of columns we have is 4. Here you can count 1 2 3 4. 4 columns we have. 3 rows, 4 columns, and the distance is 1. So distance, it has to be 1. They have given the distance. The distance will be helpful when we are calculating the this one. What do we call Euclidean? This one. Euclidean distance has to be less than or equal to d. They have given, right? And also they have mentioned that it is guaranteed that the sum of n into m over all the test cases does not exceed 4 into 10 to the power of 6. 4 into 10 to the power of 6. 1 is 6 or 10 to the power of 6, right? So this is fine. I think the question is completely clear, man. They have mentioned crystal clearly every point, right? So I hope I have read the question correctly, or in a easy way, so that it will be easier for us to further discuss the approach and other stuff, right? So here in this case, what we'll do, we have this one, 3 rows, 4 columns, as well as distance is 1. Distance, we'll be making use of the distance. It will be very helpful or the handy when we are calculating the Euclidean by Euclidean formula or Euclidean distance. It has to be less than or equal to d they have given. So we have read the question multiple times, right? So I hope this one, what do we call, the input part is completely clear. For this particular this one input, we have to get the output 2. Nothing but the 2 distinct valid routes are there to climb from bottom row to top row for the Igor, or Igor, whatever you call, right? So for him, we have for the Igor, he has 2 valid distinct valid routes to climb from bottom row to this one, top row, accordingly with the condition that they have given, or accordingly with this input, accordingly with this input, right? Let's check the same. Let's discuss the approach now. I hope the input part and the question part is completely clear, man. If you are clear with the question, then it will be easier for us to go with the approach, right? So then if we understand the approach properly, if our approach is completely clear, then we have to articulate the same thing in the form of code. After discussing the complexities, this one approach and the complexities, whatever we discussed in the approach, that itself will be articulating in the form of code. So now the approach is important. We are done with the question. Let's discuss the approach and the complexities. Now let's discuss the approach first. So in the approach, first thing that I want to say is we will be going with the binary search along with the DP. So we'll be making use of the binary search along with the DP, and also we'll be going with the prefix sum as well, calculating the prefix sum. So calculating the prefix sum is required as well. So this we will get to know when we write the code, the prefix sum part, right? So this one, let's understand this one approach step by step first using the binary search along with the DP. Binary search because we'll be going with the lower bound and upper bound, man. So that is the reason we'll be making use of the binary search for this particular problem. So here let's come to the example part. Let's come to the example part here. So n we have 3, n we have 3, m we have 4, and d 1. Nothing but this is rows, this is column, and this is nothing but distance. Right here, row 0 we have this one, row in the row 1 we have this one input, row 2 we have this one. So output that we need to get here is 2. So the output that we need to get here is 2 accordingly with the question they have given, right? So in the output part they have given 2. So the distinct distinct valid routes from for the Igor to climb from bottom row to top row is 2. So that's what they have given here, right? So 2. So let's come to the this one step by step explanation part. Let's move on with the step by step explanation here. First step here is we scan the matrix and collect all the possible positions. All the possible positions, when I say, it's the column indices I am speaking of, right? It's the column indices I am speaking of. Column indices means this one. So this part, this part, this one, column indices I'm speaking of, right? So don't get confused here. We scan the matrix and collect all the possible positions, column indices, where x is present. Where x is present. Where all the x is present here? See, 0, 1, 0, 2, 0, 3, 0, 4. This one, 1, 0, 1, 1, this one, 1, 1, this one, 1, 2, this one, 2, 1, and 2, 3. So here x is present, right? X is present here. So within the column here we have 1, 3, 1, 2, and 0, 1, 3. 0, 1, 3. These are the things that we will consider basically. Just give me a second here. What happened to this one? Yeah. So row 2, 1, 3. Row 2, 1, 3. So just give me a second here. What happened? This one. Yeah, this is fine. Row 2, 1, 3. Row 1, 1, 2, and this one. We scan the matrix and collect all the possible collections. Nothing but the column indices. We are getting the column indices here, right? Where x is present. Where x is present. Right, so this is fine. Just give me a second. Did I miss something here? Did I miss something? No, right? I didn't miss anything. I believe I didn't miss anything. Just give me a second here. Where x is present. Yeah, this is fine. Row 2, 1, 3, row 1, 1, 2, and row 0, 0, 1, 3. This is fine. So next, exposition of 2. Exposition of 2 is 1, 3. Exposition of 1 is nothing but 1, 2. Exposition of 0 is nothing but 0, 1, 3. So these are the values that we got. So exposition of the index 2, exposition of index 1, and exposition of index 0 is this one, 1, 3, 1, 2, and 0, 1, 3 respectively. So this is the first step. So let's move on with the second step. First step is simple. Let's move on with the second step. So here we will be initializing the DP on the bottom row. So we are going with the bottom up approach. Because Igor we have to count the number of steps, number of valid distinct valid routes that Igor can use to climb from the bottom row to the top row. So here you would have already guessed that if we are going with the DP, quite obviously we'll be going with a bottom up DP. Bottom up DP, right? So bottom up approach, sorry, bottom up DP approach. So here from each x on the bottom row, from each x on the bottom row, we can either use it alone or pick two holds. From each x on the bottom row, we can either use it alone or pick two holds. Here, where x is present here, 2 comma 1, this is 2 comma 0, this is 2 comma 1, 2 comma 1 x is present and 2 comma 3 x is present. 2 comma 1 x is present and 2 comma 3 x is present here in this case, right? So let me do one thing. What we are doing here, we are initializing the DP on bottom row, nothing but we'll be going with a bottom up approach here, right? So we will initialize the DP on bottom row. For each x, what we'll be doing, for each x on the bottom row, we can either use it alone or pick two holds. This is very important. We can either use it alone, or we will be using it alone mostly, or we can pick two holds. So this sentence is very important, right? So this word basically pick two holds they have given here. We can either use it alone or we can just pick two holds. We can either use it alone or we can just pick two holds, right? So between, let's consider 2 comma 1 and 2 comma 3 because x is present on the this one 2 comma 1 and 2 comma 3, right? So between 2 comma 1 and 2 comma 3, let's apply the Euclidean formula here. Distance, Euclidean distance, right? Nothing but here this what do we call here? First one, suppose consider this one x, this one y, this one xi, this one yi. The formula is nothing but here in this case xi minus x plus yi, this one yi minus y, square root of xi minus x plus yi minus y. So this is the Euclidean formula. We know this one to calculate the distance, right? Euclidean distance. So this will be basically 2 minus 2 plus 3 minus 1 whole square. 2 minus 2 whole square plus 3 minus 1 whole square. Nothing but here in this case 0 plus 2 square. So 2 square will lead us to the square root of 4. Nothing but we got the output 2 here. We got the output 2 here. So 2 is greater than d. D in the question we have 1. So here you can clearly see D they have given 1. Strictly they have given 1 here. 2 which is greater than D. So whatever 2 answer that we got here, 2 is greater than D. So it is not reachable. So quite obviously it is not reachable here in this case. It is not reachable. When we put the Euclidean distance here, simple formula. So to calculate the Euclidean distance, so it has to be less than D. While reading the question, I have read this one multiple times that it has to be less than D at any cost. It has to be less than D at any cost. Here in this case, 2 is greater than D and it is not reachable. And it is not reachable. Right, so here in this case, so dp of 1 will be 1, dp of 1 will be 1 and dp of 3 is also 1. We are updating here basically, right? So here in this case we are updating. What happens here means, so here see we got 2 here, right? So for you the question might have arisen that how did we get dp of 1 equals 1 and dp of 3 equals 1? We have got the answer 2. How we are taking the value 1? Because they are not reachable. 2 is greater than d and they are not reachable. So each can only be picked alone. Each can only be picked alone. Here dp of 1. So here this can be broken down. 2 can be broken down into 1 and 1. This is nothing but here 2 comma 1 where x is present and 2 comma 3 where x is present at the second third row, basically row 0, row 1 and row 2, right? 0 indexed row 0, 0, row 1 and row 2. In the row 2 here x is presented 2 comma 1 and 2 comma 3. So we are breaking down the 2 into two steps. Dp of 1 equals 1 and dp of 3 equals 1. This is where the dp plays a major role. This is the reason we'll be making use of the dp basically, right? So here no combinations are possible. No combinations are possible here in this case. So total of 2 base paths to start with. We have total of 2 base. We have total of 2 base to starts with. We have total of 2 base to starts with, right? So here we are done with the step 2. I hope the second part is completely clear, man. Easy to understand, right? So first two steps are completely, I hope first two steps are completely clear. Let's come to the transition to row 1 part. Let's come to the transition to row 1. We have to go with the transition for the row 1, right? So let's see. Now we want to move from holds in row 2 to row 1. Row 1 means here this one, row 0, row 1 and row 2, right? So we are done with the row 2. So now we are considering this one, row 1. Here where is x present in the row 1? This one, 1 comma 1 and 1 comma 2. So here 1 comma 0, 1 comma 1, 1 comma 2 and 1 comma 3. Where x is present 1 comma 1 and so x is present at 1 comma 1 and x is present at 1 comma 2. X is present at 1 comma 1 and x is present at 1 comma 2. So let me come here. Now we want to move from holds from row 2 to row 1. This is fine. Valid transitions must satisfy. We have to move to the higher or same row. We have to move to the higher or same row. We are going with the bottom up, so we are done with the row 2. We are done with the row 2. As we want to move higher, or same row, we are done with the same row. We are done with the same row. We considered all the x's in the this one, row 2. So now let's go with the row 1. Now let's go with the row 1 where x is present. So here that is 1 comma 1 and 1 comma 2. 1 comma 1 and 1 comma 2. Within 1 comma 1 and 1 comma 2 x is present. Within 1 comma 1 and 1 comma 2 x is present. Again I'm stressing on it. So within 1 comma 1 and 1 comma 2 the x is present, right? In the matrix basically. Here distance has to be less than or equal to d. Distance has to be less than or equal to d means d we have the value 1. Distance has to be less than or equal to d here in this case. Previously in the step 2 we have got 2 d's. Answer 2 which was greater than d. Here again distance has to be less than or equal to d. Let's check. We have to apply the Euclidean algorithm again, right? So let's check. So let's do one thing. So just give me a second here. We will check from each hold in row 2. We will check from each hold in row 2. 1 comma 3 to each hold in the row 1 1 comma 2. So this one 1 comma 2 and 1 comma 3 I have said this one multiple times, man, where x is present 1 comma 2 and 1 comma 3. So we will check for from each hold in row 2 1 comma 3 to each hold in row 1 1 comma 2. Means here in this case again I'm telling in row 2 where the x was present basically in this one 2 comma 1 and 2 comma 3. Here in the row 1 1 comma 1 and 1 comma 2. So we have to check from 2 comma 1 to 1 comma 1 entirely including row 2 and row 1 now. Including row 2 and row 1 now. Now we have to apply the Euclidean formula. Right? Now we have to apply the Euclidean formula again. Let's check from 2 comma 1 now. Let's check from, as I have said, we have to consider two rows now. We have row 1 also considered this time, right? So we were done with the double x that was present in 2 comma 1 and 2 comma 3. Now we are considering the row 1 as well, 1 comma 1 and 1 comma 2, right? So now we are considering from 2 comma 1 to this one, these four things: 2 comma 1 2 comma 3 2 comma 1 comma 2 and 1 comma 1, right? 2 comma 1 to 1 comma 1 basically. Don't get confused here, right? So we are considering two rows now, right? We are considering two rows now. So here we will check whether reachable holds in row 1, whether reachable holds in row 1. For 1 comma 1, for 1 comma 1 we are checking for 2 comma 1, right? 1 comma 1 and 2 comma 1 we are applying the Euclidean formula. We are applying the Euclidean formula. One second here. Yeah, we are applying the Euclidean formula. So this will be 2 minus 1 whole square plus 1 minus 1 whole square, right? 2 minus 1 whole square will be 2 minus 1 whole square will be 1 square. This 1 minus 1 will be 0. Let's go this one, ignore this one. This is nothing but square root of 1. 1 square, square root of 1. We are left with square root of 1. We got the answer 1. So D has to be the value has to be less than d here in this case. So see here, distance that we got here is 1. Less than, it should be less than or equal to the Euclidean distance. So here in this case we got 1 which is equivalent to the d, which is equal to the d. So this one we can consider. This one we can consider. So it is possible from 2 comma 1 root to 1 comma 1. 2 comma 1 to 1 comma 1. So next we have 1 comma 2. Here also x is present in the row 1. Here also x is present in the row 1. We have to go with the same thing again from 2 comma 1. So let's go with the same formula. 2 minus 1 whole square plus 1 minus 2, or this one bigger number we'll consider, right? 2 minus 1 whole square for the Euclidean. So we'll go with this one basically, absolute value. So we shouldn't be getting the negative value, right? When we are calculating the Euclidean distance. So we are going with the absolute value. Either you can go with the 1 minus 2 whole square as well. So it doesn't matter, 2 minus 1 or 1 minus 2. So here in this case it will be 1 square plus again 1 square. This will be 2. Square root of 2. Square root of 2 is nothing but 1.41 we get. So here this is greater than 1. Greater than the distance is greater than the Euclidean distance, d, small d, right? So d that they've mentioned in the question, it shouldn't be. So this miserably fails here. This miserably fails here. We are not considering the second one here. So I'll just cut this one entirely. So the only row, only 1 comma 1 is reachable. So from 2 comma 1, 1 comma 1 was reachable. From the row 2, 1 comma 1 is reachable, right? So this one will consider 1 comma 1. So let's move on with the next part here from 2 comma 3. Since we considered 2 comma 1, we are checking reachable holds in row, right? So we checked from the row 2, we checked 2 comma 1 where x was present. In the second row, x was present in 2 comma 3 as well. We have to check for 2 comma 3 as well. Now we have 1 comma 1 and 1 comma 2 checking with 2 comma 3. So here I'll come 2 comma 3 will apply the Euclidean formula. This will be 2 minus 1 whole square and 1 minus 3 whole square. This one. 1 minus plus 1 minus 3 whole square. This will be square root of 5. Square root of 5. Square root of 5 gives 2.24 because distance here, this is nothing but the distance which is greater than d. It should be less than d actually. D we have 1, right? D we have 1. So this miserably fails. Let me cut this one. This doesn't satisfy the condition. Let me come to here 1 comma 2. 1 comma 2 same again we'll consider 2 comma 3. This will be 2 minus 1 whole square plus 2 minus 3 whole square. 2 minus 1 whole square plus 2 minus 3 whole square. This will be again, so this will be what absolute value will be considering. This will be, we'll consider this one in the positive itself, right? Even though we get here 2 minus 1, 2 minus 3, this will be minus 1. It will be 1 square. So it will be, we'll consider the positive value itself, not the negative value basically, right? So this is fine. So what we'll do here, let me do one thing. Or you can just consider this in this way also. Minus 1 whole square will be minus 1 into minus 1. It will be 1 actually. Right. So here we are left with 1 plus 1 nothing but square root of 2. Square root of 2 is nothing but 1.41. So 1.41 again it is greater than d. It is greater than d. This also miserably fails. This also miserably fails. So 2 comma 3 cannot reach on hold in row 1. It cannot reach on hold in row 1. Right. Only 2 comma 1 can reach hold with 1 comma 1. With 1 comma 1, that is the only thing that was possible, right? So that is the only thing. This 1 comma 1 was reachable because we got the value 1 here which was equivalent to the value of the d, right? So I hope this part is completely clear. Calculation part is completely clear. Next let's discuss further. So we are left with only one transition that is valid, nothing but from 2 comma 1 to 1 comma 1, right? So 2 comma 1 to 1 comma 1. Now we will update the dp of 1 for row 1. We'll update the dp of 1 for the row 1. Here just give me a second here. Yeah, now we will update the dp of 1 for the row 1. So since from 2 comma 1 we had dp of 1 equals 1, that one way flows into 1 comma 1. Here in this step, if you remember, where did that go? dp of 1 we have 1 here. dp of 1 equals 1 and also dp of 3 equals 1, right? So if we consider this one, since 2 comma 1 this one was for 2 comma 1 and this one was for 2 comma 3. So here I have written the same thing. Sorry, just give me a second here. 2 comma 3, I have written the same thing here as well. So here you can clearly see here, right? So since from 2 comma 1 we had dp of 1 equals 1, that one way flows into 1 comma 1. That one way flows into 1 comma 1. So now what we have, dp of 1 equals 1 and dp of 2 equals 0. Now here let me come to the 8th page here. This one, not even 9th page, right? So here now we have dp of 1 equals 0, dp of 2, this was not possible at all. So this value will be quite obviously 0. Just give me a second. What happened to this one? 1 second. So here now we have dp of 1 equals 0. This one was not possible at all. This will be equals to 0. Here we have one way. Basically, that is one transition that is valid from 2 comma 1 to 1 comma 1. Right. So I hope this part is completely clear. Let's move on with the next step. Let's move on with the next step. So now we are going from transition to this one, row 0. Now we are going from transition to row 0. First we considered 2 as we have to climb, as Igor has to climb from bottom to top. We considered the row this one, row 2. Next we considered row 1. Then we saw all the transitions from 2 to 1. We applied Euclidean formula and we saw only one route was possible, that too from 2 comma 1 to 1 comma 1. Now we have to see the transition to the row 0. Now we have to see the transition to the row 0. So again, let's compute the distances. Here we have to consider 3 rows now. This time we have to consider 3 rows, 0 1 3, 0 1 3, 0 1 and 3. So this one, what we will do here in this case, we will be going with 0 comma 0, this one 1 minus 0 plus 1 minus 0. So I hope this is clear, right? So 1 minus 0, so just give me a second here, did I miss anything here? So from DP on row 1, we have only one path, that is nothing but the 1 comma 1, right? From DP on row, this one we have only one path, nothing but in the row 1 we had only one path, right? From 2 comma 1 to 1 comma 2. So we'll go with 1 comma 1 here. So we have to consider 1 comma 1. This was the valid route from 2 comma 1 to 1 comma 1. So we have to consider 1 comma 1 here. In this case, when we apply the Euclidean distance or the Euclidean formula, this will be 1 minus 0 plus this one, 1 minus 0 or 0 minus 1, you can consider in either way. So this will be 1 plus 1, this will be square root of 2. Again 1.41 we got. So this is greater than D, which miserably fails. D's value is 1, so this miserably fails here. Let's go with 0 comma 1. Again we are performing same thing on 1 comma 1. This is the only valid this one root which we found in the row 1 basically. So this will be again what do we call, 1 minus 0 plus 1 minus 1, right? So this will be 0, quite obviously. 1 minus 0 is 1. 1 whole square will be 1 itself. Square root of 1 is, again we found here this one 1, we found here this one as this one 1. So here in 0, where x are, where is x present, here we have 0 comma 1, 0 comma 0, 0 comma 1, 0 comma 2 and 0 comma 3. X is present at all the positions, right? 0 comma 1, 0 comma 2, 0 comma 0 comma 0, 1 2 and 3. X is present everywhere in the this one, all the 4 columns, or all the this one in all the columns in the first row, right? So here in this case, uh, which one satisfies basically here in this case? So 0 comma 1 satisfies the condition, because we have got the value 1 when we applied the Euclidean formula. We have got the value 1 here, 1, we got the value 1 here, which is equivalent to the D. D's value is 1 and distance value is also 1. Distance has to be less than or equal to D. So here in this case, this is valid. So now we got one more along with the 1 comma 1, we got in this one, what do we call, from 2 comma 1 we had 1 comma 1. So 1 from what do we call, while computing we have got 1 comma 1 which was valid basically, right? So here let's go with 1 comma 3. Now again we are calculating from this one, right? So this will be Euclidean formula, 1 minus 0 plus 1 minus 3, or 3 minus 1, sorry, yeah, same thing. So this will be absolute value. Again I'm telling 1 minus 0 is 1 square plus 2 square, nothing but here on this square 1 plus 4, this will be square root of 5. Square root of 5 will get 2 point something, 2 point something, something, I'll write it as something itself, 2 point something, right? 2 point something means D we have 1 here, so this will be greater, and this miserably fails. Will not consider this one as well. Will not be considering first one, will not be considering the third one, will only go with the second one because we have the value 1 here. So we got only reachable this one as 0 comma 1, only reachable as 0 comma 1. In the row 1 only reachable was 1 comma 1. From 2 comma 1 only reachable in the 1 comma 1, this one row 1 was 1 comma 1, this is row 2. From 2 comma 1 only this thing, only reachable was 1 comma 1. From 1 comma 1 only reachable was 0 comma 1. From 1 comma 1 only reachable was 0 comma 1. So this is the route we got, this is the route we got basically, because on the bottom row a level can use up to 2 holds, right? So here now this is one path, this is one complete valid path we got from this one, bottom row to top row, bottom row to top row. So we have discussed every step clearly by applying the Euclidean formula from the bottom row to the top row, by applying the DP as well. And we will be going with the prefix sum. Prefix sum part you will understand when we write the code correctly. I can assure it. I can assure it, or I can bet it that this one prefix sum part you will be understanding while we write the code. Here in this case, only one valid path found for the Igor to climb from this one bottom row to top row, nothing but from 2 comma 1 to 1 comma 1. This is nothing but the row 2, this is nothing but the row 1, this is nothing but the row 0. 2 comma 1 to 1 comma 1 to 0 comma 1. So this is fine. Let's move on with the next step here. Because on the bottom row, level can up to use the this one, use up to 2 holds, right? On bottom row, a level can use up to 2 holds. Igor has 2 hands, right? He is not having the one hand. He is a human being and is having the 2 hands, right? So because on bottom row, a level can use up to 2 holds. Here in this case, Igor has 2 hands. So 2 comma 1 and 2 comma 3 we can use it together. 2 comma 1 and 2 comma 3 we can use it together. We used individually, right? While telling the approach, I said somewhere something. I just give me a second here. Where x is not this part, not this part. So here, yeah, here this one, step 2. With while discussing the step 2, from each x on bottom row we can either use it alone. We use 2 comma 1 and this one 2 comma 3 alone. We use 2 comma 1 and 2 comma 3 alone, or we can make use of the, we can pick 2 holds. We can pick 2 holds. Now we will use 2 comma 1 and 2 comma 3 at a time. We'll be picking 2 holds at a time, nothing but 2 comma 1 and 2 comma 3 at a time. So that's what here we'll be doing basically, right? So that's what we'll be doing here. So here we will go with 2 comma 1 and 2 comma 3 when used together. So now from the above combination, Igor can reach from 1 comma 1 from 2 comma 1, from 1 comma 1 from, quite obviously from 2 comma 1 Igor can reach 1 comma 1. We have already seen this one, right? And from 1 comma 1 Igor can reach this one, 0 comma 1. So this one we have seen. From 2 comma 1 Igor can reach 1 comma 1, and from 1 comma 1 Igor can reach the this one, 0 comma 1, which is valid. So routes, this one, valid routes is nothing but route 1 from 2 comma 1 to 1 comma 1 to 0 comma 1. So again, while we consider 2 comma 1 and 2 comma 2 together, this one also we can, right? We can pick 2 holds together at a time. So this will be 2 comma 1 once and 2 comma 3 once, right? This is 2 comma 1 once and 2 comma 3 once. So this will be 2 comma 1 2 comma 3 at once to 1 comma 1, nothing but from the row 2 to row 1, then to finally from 1 comma 1 we can reach 0 comma 1. So this will be one valid route by considering these 2 holds together, 2 comma 1 and 2 comma 3. So now this will be one valid route. First one will be quite obviously one valid route, and the second one will be one valid route as well. So when we sum up this one, 1 plus 1, we got 2 valid routes, nothing but 2. So the value that we got here is 2 valid routes. So Igor can climb from bottom row to the top row. Igor can climb from bottom row to the top row. The valid routes will be quite obviously 2. He will be having 2 valid routes to climb from bottom row to the top row. Here it will be 2. One is from 2 comma 1 to 1 comma 1, from 1 comma 1 to 0 comma 1. So the second route is nothing but 2 comma 1 2 comma 3. This we are picking 2 holds together, and he can climb to 1 comma 1 and from 1 comma 1 to 0 comma 1. So this will be one valid route, and this will be one valid route that will lead to 2 valid routes. So the output that we got here is 2. Will return total valid routes, nothing but the 2. The output that we got here is 2, which is equivalent to the output that they have mentioned for the this one, example 1 in the question. Example 1 in the question for this particular input we are speaking of, right? So let me change the color, you will understand this one. So this one, what happened to this one? Yeah, from this input for this input I'm speaking, we got the output 2, which is equivalent to the output that they have given for the example 1, right? So here this one 2 equals 2 here. Now our approach works absolutely correct. Now our approach works absolutely correct in this case. So I hope the approach part is completely clear. Only thing that we have to understand here is, so there are only 3 steps, man. One thing, we have to this one, consider where all the x is present. We have to consider this one position where all the x is present. Next we have to go with the dp. Using the dp will be basically based on the code that we write. So let's keep the dp aside for now. So first thing, we have to find where all the x is present. Then we have to apply the Euclidean distance or the Euclidean formula, and then we have to find all the valid routes. We have to find, or we have to return all the valid routes that we have found. 3 steps, only 3 steps. main three steps. So whatever we have discussed now, I hope the approach part is completely clear. Let's quickly come to the final part here. Let's quickly come to the final part, or let's discuss here itself, right? So let's calculate the this one. What do we call? Um, I mean, let's discuss the complexities now. So here in this case, what will be the time complexity for the code that we'll be writing? So the time complexity here would be big O of n into m log this one m. Big O of n into m log m. You would have asked why this will be basically n into m log m. Uh, because we'll be making use of the binary search on exposition. So if you remember exposition of something, three expositions, right, we went with initially, right? So we will be performing dp. So we sorry, binary search, not the DP. So we'll be going with the binary search on exposition of R. This may be any value. Just consider R for now. We'll be applying the binary search on R and the DP propagation. We'll be going with the DP for the caching purpose. For the caching purpose, we'll be making use of the DP and we'll be going with the binary search as well. So here the overall time complexity would be big of n into m log m. So n into m log m. So this will be our time complexity basically, right? So this will be our time complexity. What would be the space complexity here? Space complexity would be here big O of n into m. N is nothing but here in this case rows, we know this, and m is nothing but the columns. N is nothing but the rows here and m is nothing but the columns here. Big of the space complexity is big of n into m because we are storing all the positions and the prefix array. Prefix array part you will come to know when we write the code. I bet it, I assure it, right? So you'll get to know the prefix arrays, right? So to calculate the prefix sum, basically here we will be storing all the positions and the prefix arrays plus prefix arrays basically, right? So the overall space complexity would be big O of n into m. So the overall space complexity would be big O of n into m. So this will be our space complexity and this will be our the time complexity. So the time complexity would be big of n into m log m and the space complexity would be big of n into m for the code that we'll be writing in the future. So I hope the coding part, I hope the complexities part is completely clear. Now, as we are completely familiar with the approach and complexities, we are good to write the code. Let's start writing the code. So let's start writing the code. Now, I want to tell you one thing. We'll be making use of the fast scanner, I mean fast reader and fast input and fast output. So let's import the input output package here. So I'll just go with import java.io.star. So also we need the utility, right? Utilities. So I'll just go with import java.util.star. So this is fine. So this has to be star man, not x. So this is fine. So let me do one thing. Let's go with the main class. So I'll just go with public class this one main. So let me go with public class main. Within this main class, we are going with the fast scanner and we are going with the print writer. Fast scanner for the input part, reading input, and print writer for the output, fast output. Right, and also we'll be making use of the modulo that is constant. Modulo that is constant. 4 into 10 to the power of 6. They have mentioned, right? That should not exceed 4 into 10 to the power of 6. They said. So here we'll be going with a fixed modulo constant as well. So here first let's go with the fast scanner. This will be static fast scanner. So this one sc equals new fast scanner. This one is fine. Next, let's go with the print writer. This will be static. Here in this case, print writer. So this one will be pw equals new print writer. New print writer of new buffered writer, new output. This one stream writer of system.out. So let me pass here system.out. This is fine. So I hope this is fine. So next let's go with the modulo constant, right? As I've said, constant modulo value. So I'll just go with here static. So this has to be constant. So I will make use of the final keyword here. This one will be int. So let me go with mod, variable mod, and assign this one to double 98244 353. So it shouldn't exceed basically 4 into 10 to the power of 6, right? So you can just go through the question once. There you can just go through the constants, right? So here next step is we have to read the number of test cases. Let me give main here. I'll forget this one, I know. So within this one, we don't have to make use of the this one input output exception, right? For this particular this thing. No, we don't have to. This is fine. So let's read the number of test cases here. In this case, it will be sc dot next int. Sc dot next int. This is fine. So we are just reading the number of test cases. After reading the number of test cases, we have to create the solution object. For creating the solution object, let me go with solution so this one. Let's go with new solution of this one will be sc nothing but the scanner and pw nothing but the print writer. So we are just creating the solution object here. Next step, we have to solve the each test case. We have to solve the each test case, or we have to check for each test case. So for that one, I'll just go with while loop. We have to at any cost, right? So for that reason, I'll be making use of the while loop here. T decrement. So if this is greater than 0, then I'll just give so dot solve. So dot solve. This is fine. So here in this case, we have to close the writer after all the test cases. So we don't have to, we are done with the writer. Once we are done with the writer, we don't have any use, right? So at that point, we have to close the writer, right? After all the test cases mainly. So this one, I'll just give pw dot close. I'll just make use of the close operation. Right, I hope this is clear. So this is it for the input output part. So we have to implement this one fast scanner part, basically reading the input for reading the input fast. So we'll be going with a fast scanner. Let's implement that one at the last. For now, we are done with the input output. Let's let's focus on the logic part basically, right? So here I'll just give static class. So what did I do here? Class. So let me go with the solution, name solution, right? So within the solution class, so what we'll do, let me go with fast scanner sc and again print writer pw. So here this is fine, and also let me go with solution of fast scanner, this one sc nothing but the scanner, and print writer nothing but the pw. This is fine. So within this one, this dot sc, let's assign this one to sc, and this dot pw, let's assign this one to pw. This is fine. So let me come out of this one entirely. So let's mainly now, so this was also basically related to the input output itself, sorry, right? So now we are into the logic part basically. So let's go with a name solve. So void solve. So here within this function, what we'll do, solve function. So here in this case, first let me assign n to scanner dot next int here. N is nothing but the number of rows. M is nothing but the number of columns. Usually we'll go with M and N. Don't get confused here. N is nothing but the number of rows. M is nothing but the number of columns. So this one will be again sc dot. So sorry, not I should be capital here. So here also, why I it is taking basically this one. This has to be capital, right? So this is fine. Next int. And also distance nmd we have in the input, right? So distance for this also we have to give sc dot next int. So scanner dot next int. We have to move towards every input this one, right? So here this is fine, man. Why this is not taking? Oh, this is fine. Yeah, we have to read the mountains grid. We have to read the mountain grid. Sorry, for that one, I'll be making use of the grid variable. So this is 2D, right? So this one, let me go with g equals new char of this one will be n and this one will be empty. This is fine. Let me come out of this one entirely and let me go with the for loop. This will be int I equals 0, I less than n, and I plus plus. So this is fine. uh, this one will be g of I, this one equals sc dot next int, this is fine, and we have to convert this one to the char array, so this will be to char array, so this is fine. This is it. Next part is, let's move on with the this one. We have to check all the expositions in the for each row accordingly with the approach. Now we are going with the approach, right? First here we are just in the line number, this one what do we call, line number 27. Basically we are reading the mountain grid. We have to read the mountain grid. The next step is main logical part starts from here. So basically what we did, everything that we discussed in the approach, everything that we discussed in the approach by considering the first input or the first example from the question, we will apply here, right? So we'll articulate the same thing in the form of code here. Now we have to store the expositions for each row. So for storing, I'll just make use of the list here. So this, it is everything is integer, right? So let me pass the integer here, data type. So here in this case, array. So let's go with a exposition equals new this one array list. So we are going with a list, right? Array list. So this is fine. So the next step here is, let's go with the iteration part. So this will be int I equals 0, I less than n, and let's go with I plus plus. So next let's go with exposition, iterated value of the exposition equals new. So let me give array list. That's it, right? We are just assigning this one to the iterated value of the expression to the array list, new array list. So here we have to go with go for the each row, right? So let's consider j. So we have to store the column index first. We have to store the column index. For that one, let's consider the this one j, variable j. So I'll just go with int j equals 0. So column nothing but m, j plus plus, n is rows and m is column, right? So we are iterating, or we are going with the each column. So we have to store the column index, right? So here to store the column index, I'll just go with grid of I and j if it is x. If it is x, then what we need to do here in this case, x position of I, this one, let's add this one to, let's add this one, this will be j. So we are storing the column index, we are storing the column index here. So by this one vivo is, so at least I would have given vivo ip calling. So not the vivo ip or not the vivo is, this is vivo id, nothing but the void here. So this is fine. Let's come out of this one entirely. Now we'll be going with the dp. So now we'll be going with the caching part or the dp of j, nothing but the number of ways to reach the position j in the current row. How many number of ways, we have to calculate how many number of ways to reach the position j in the current row, right? For that one we'll be making use of the dp, right? So here on this scale, let's initialize the dp array first. This will be dp equals new int of m, dp equals new int of m. This is fine. Let's initialize the bottom row, nothing but n minus 1, the last cell, the last cell. We have to initialize the bottom row, right? The last cell, nothing but the n minus 1 here in this case for int j. So this will be x position of within the array, this will be n minus 1. This is fine. So within this for what did I do here? What did I do, man, here? So why this is taking like this? So yeah, here itself I have given. So after this I have to give, sorry. Yeah, within the for loop, we have to go with the valid range of column indices that is reachable from j using the Igor span. From using the Igor span, we have to go with the valid range of column indices that is reachable from j, right? So for valid this one, we'll be going, we can go with the this one max and min. To calculate the max and min, this one we can just make use of the math operations, nothing but math.max and math.min. Here let me go with int l equals math.max of 0 comma j minus d. This is fine. So here r equals Again we have to calculate min as well. So let me go with the math.min of, first we have to consider the rows, nothing but the m minus 1, the last row. So this one has to be m minus 1 comma j plus d, j plus d, right? So we are considering the column here plus distance. So this is fine. So the next step is we have to count the other holes within the reach to pick up to two holes in the bottom row. So here if you remember, there was one valid path from 2 comma 1 to 1 comma 1 and then 1 comma 1 to 0 comma 1, right? So there another path also we considered, keeping 2 comma 1 means we what we did, we went with the two holes, right? We went with the two holes in the bottom row directly by considering 2 comma 1 and 2 comma 3 at the this one, by considering 2 comma 1 and 1, 2 comma 3 at a time with 1 comma 1 to 0 comma 1. So those were the two valid paths for the first this one first example. So for that one, to count the other holes within the reach to pick up two holes in a bottom row, we have to write the code. That's what that we have to implement or articulate in the form of code. Here what we will do, we will be making use of the lower bound and upper bound here in this case for this one. So we will be performing binary search, we will be performing binary search, nothing but lower bound and the upper bound, right? So before performing the binary search here, nothing but the lower bound and the upper bound, before using that, so write the let's write the lower bound and the upper bound this one function first. So here in this case, let's go with the binary search lower bound first. So here let me come here. So let me come here. So let me do one thing. First let's go with the binary search lower bound. Here lower bound will be lower. So this will be bound. So here within the lower bound, let me do one thing. We have to pass the list of integer. We have to pass the list of integer. I'll just consider the variable name or the parameter, this one name list here, and also the value which is of the type int. So this is fine. And within the lower bound, what we will do, let's perform the binary search. Initially, I'll just consider variable L to 0, left and right. So this one will be 0, right to the last, this one, or the list size, or the size of the list, right? So this one will be list dot size. So this is fine. The next step is pure binary search here, while left less than right, then we have to calculate the mid. This will be int mid equals left plus right. So this one will be by 2 to calculate the mid basically, right? So next step is here if list dot, let's go with the get operation here, nothing but list dot get of mid here. If it is less than val, then we will assign L to mid plus 1. If you know the binary search, we are just going with the pure binary search here, right? If you don't know the binary search, you can just go through the some 24 important algorithms list that I have uploaded, right? So that I have uploaded on the playlist 24 important algorithms. You can just check that one, right? You can just check that playlist. I have expand most of the important algorithms including binary search, right? Binary search, there are so many algorithms that I have explained there, all the sorting algorithms, binary search, and other algorithms, right? Graph algorithms, so some of the algorithms related to graph, so those algorithms I have explained. You can just go through that one, right? You'll get it. So here in this case, else we will assign R to mid. This is fine. Finally we will return left or the L here. This is for the lower bound, that is the reason we are returning L here. This is fine. Let's do one thing now. Let's go with the upper bound. Let me copy the same thing entirely. Let me copy this one same thing entirely and let me make the necessary changes here. So this one will be, instead of lower bound, this will be upper bound. So let me give upper here. This is fine. List of integer, list, this remains same, right? This remains same. This L equals 0, R equals list dot size, this also remains same parameters, while left less than or this also remains same. Let mid equals left plus R by 2. So this also remains same. If list dot get of mid, here instead of less than val, this has to be less than or equal to val. As we are going with the upper bound, if list dot get, we will be making use of the get operation mid less than or equal to val, then we'll be assigning left to mid plus 1, else R equals mid. This remains same. and also here also this one, what do we call, we will return L itself, we'll return the L itself, right? So I hope this part is completely clear. I hope this part is completely clear. Now we are left with the this one, what do we call, we are left with the we have to implement the lower bound and the upper bound, right, within the main function, within here, within the solve function, this one, right, in the line number 41. So before doing that, let me tell you one thing. We are left with the this one, fast scanner input output implement, this one implementation. This one I'll not be typing. Let me copy paste this one. This is related to input output, not the logic part, right? So let me copy paste this one. You can just pause the video and have a look into it, right? Just give me a second here. So here, let me paste the this one. This is nothing but so this is what I said. This is nothing but the input, this one, input output implementation. This is nothing but the fast scanner implementation, basically related to the input output. This is not the logical part. So you can just if you want to make use of the, or if you are making use of the same template, then you can just go with this, right? So this is just for the fast input output. You can just make use of this template, right? So here this is for the implementation of the fast scanner. So here we have assigned this one, fast scanner is it to the new fast scanner, right? This is nothing but the implementation of this one. This starts from line number 67 to 87, right? So I hope this part is clear. This is not related to the this one logical part. This is not the logical part. Basically this is just related to the input output. So you can just pause the video and have a look into it, right? So that is the reason I didn't type. So let's do one thing. We are done with the lower bound and the upper bound part here. Let's continue with the same here. Let's continue with the same here. So here in this case, now we have to make use of the lower bound and the upper bound. So here we went with the this one, what do we call, just give me a second here. What did we do, man, here? So we are done with this one, right? So we have to count the other holes within the reach, or to pick up to 2 holes in the bottom row. So here I can just give int L equals, so let me go with lower bound of this one will be x position within the array n minus 1, the last column, the last cell, basically, right? So along with the L, capital L. And also for the right, r equals, let's go with the upper bound of this one, x position, upper bound of x position, the last cell, nothing but the n minus 1, the last column, this one, last cell, nothing but n minus 1. This will be r instead of L, right? So I hope this part is clear. Nothing but now we have to exclude the self. Now we have to exclude the self, nothing but I'll just go with the count, or I can just go with the CNT here. This is fine. Count equals r minus L minus 1. This is fine. The next, the final one is we have to go either solo or with another. So we have discussed this one individually. We can just consider in the example we considered 2 comma 1 to 1 comma 1, that was the one valid path. 2 comma 1 to 1 comma 1 to 0 comma 1, that was one valid path. Either we can go solo, that we went solo, or rather than solo we can go with the 2 holes as well. 2 holes means the last one from bottom, we can consider 2 expositions, means 2 comma 1, 2 comma 3 as 1, and then that leads to this one 1 comma 1, and that from 1 comma 1 path that leads to 0 comma 1 finally, right? 2 valid paths. So we consider 2 comma 1 and 2 comma 3 at once. So here the same thing, we can go either solo or with another, right? For that one we will be making use of the DP here, nothing but DP of j equals, here in this case 1 plus count is nothing but CNT be considered, so modulo mod value. So it shouldn't go out of the mod value, right? So mod we'll be considering the constant mod value here in this case. So let me come out of this one entirely. Let's continue, or yeah, let's continue here. Let's move on with the further things here. So we have to go with the maximum vertical component that is allowed to stay within the total distance d. It shouldn't exceed, the value doesn't, shouldn't exceed the d, small d, right, that they have given in the input. In our case the input was given n equals something, n equals 4, n equals 3, m equals 4, nothing but the rows and columns, rows 3, columns 4, and d we have been we were given 3, we were given 1, sorry. So every time the value exceeded 1, more than 1, we ignored that one. when we performed Euclidean distance, this one to calculate this one Euclidean distance, when we performed the this one Euclidean formula, when we applied the Euclidean formula to calculate the Euclidean distance, so every time the value that we got more than 1, we ignored. Only which was less than 0 or equivalent to the 1 we considered, right? So here in this case, that's what the same thing we need to articulate in the form of code. Let's go with the maximum vertical component that is allowed to stay within the total distance d. This one will be int vd equals, here this will be int. So let's go with the math.floor here. This will be math.floor of this one will be math.square root. So this one will be math.square root of this one will be 1l into d into d minus 1. This is fine. D minus 1. So this is fine. I hope this part is completely clear. We are just going the previous part, don't get confused. This is nothing but maximum vertical component that is allowed to stay within the total distance d. That formula we are going with this one integer of math.floor of math.square root of 1l into d minus 1. So now we have to process each row from the bottom minus 1 to top. So we are going with the bottom up approach dp. So let's go with the iteration quickly. So here I'll just write for int r equals n minus 2 r. So here r greater than or equal to 0, and let's decrement the r nothing but r minus minus. So within this for loop, let's create the new dp for the current row. So here int new dp, I'll just go with the ndp for the new dp variable name. So I'll just go with ndp nothing but the new dp. This one will be new int of m, new int of m. So we are going with the new dp for the current row, and also we are going with the prefix sums of previous dp nothing but here in this case int. So let's go with the prefix here. Let's go with the prefix here. Prefix here, this one will be new int of this one will be m plus 1 nothing but the column plus 1. M is nothing but the column, right? So we are calculating the, we have to calculate the prefix sums of the previous dp. So that is the reason we are going with m plus 1 nothing but the column plus 1. We are assigning the prefix to m plus 1 integer of m plus 1, right? So here I hope this part is clear. Next thing, let's go with the iteration part. We have to calculate the prefix sum now. So let's go with the iteration part. So this will be int I equals 0, I less than m, and I plus plus. So this is fine. So this will be prefix of I plus 1, and this will be prefix of this one I plus dp of I. So let's make use of the mod. So here in this case modulo mod constant mod value nothing but mod we have made use of, right? Made use of the variable name mod. So this is fine. Next part is after this, if you remember the approach, we have to go with the sum of dp values from next row that is reachable from j, nothing but from the row 2 we were able to reachable to this one. We have to calculate that one in the row 1. Again from row 1 we have to calculate where it was reachable from whether it is reachable from row 1 to row 2. We have to consider all the x values that is present in the row 2 row 1 and calculate the whether it is reachable or not between from the row 2 to row 1. That we have to do it by the Euclidean algorithm. So again from row 1 to row 0. So that's what we have to articulate the same thing in the form of code. Means we have to sum we have to go with the a of j nothing but we have to go with sum of dp values from next row that is reachable from j. Here in this case it will be int. So this will be a equals new int of m, new int of m, right? So this is nothing but the sum of dp values from next row that is reachable from j. So here this is for, so this is for int j, this one will be x position, this one will be r, this one will be r, right? So this is fine. So within the for loop what we will do, we will go with a capital L and we will assign this one to the, so we have to go with the math.max and math.min. We have calculated this one previously, so we know this step, right? So this one let me go with let me write the code very quickly. This one will be math.max of 0 comma j minus vd. So this kind of problems, last one or last two problems in the any division, man, this is a big headache actually. The code will be lengthier. If you don't understand or if you skip one step, then only God knows. Debugging will be difficult as well, right? So here on this case, this one will be j minus vd, j minus vd, and we have to go with the right as well. So for right, I'll just go with math.min. We have to go with the minimum value, right, for the right. So this will be column minus 1, nothing but m minus 1 comma, instead of minus vd, this will be plus vd, j plus vd. So vertical distance, right? So here this one will be a of j equals, so let's go with the prefix of r, right, plus 1, and also minus, this is the formula basically, prefix of l plus the mod value, along with this one modulo mod value. We have assigned this one to the variable mod, so this one will use this one basically. This is fine, this is fine. Let's do one thing. Let's move on with the further things. Let's move on with the further things, right? So where we left basically, this one, right? um, Modulo mod. So this one, next what we need to do, we have to go with the prefix of array a. We have to go with the prefix of array a. So how can we write that in the form of code? So let me do one thing. So int here, this one I'll just consider apre. Here this will be new int of row plus 1 for I mean column plus 1. This will be m plus 1. The next step, let's go with the iteration again. So this will be int I equals 0, I less than m, and let me increment the I, right? So this will be apre, this one will be I plus 1, this one will be apre of I, and also this one will be a of I, this one will be a of I modulo this one mod mod. So this is fine, this is fine, we are done with this part. So next, if you remember, we have to compute this one, we have to calculate or compute new dp using at most 2 holds per row. We are done with calculating for considering each hold, considering each hold, or we went with the solo, this one from the bottom, this one from the bottom row, we considered the solo position where x was present. Now we have to calculate or compute the new dp using at most 2 holds per row. So this will be for int j of this one x position. So here this one within the r. So then what we'll do within the for loop, let me go, I should have copy pasted this one again, math.max and math.min, right? So here L we will assign this one, R we have done somewhere, or let me do one thing, let me type. So here math.max of 0 comma j minus d, right? So let me assign r2. So here we have to go with the minimum value, math.min of m minus 1 comma j plus so why did this one come out? So yeah, j plus d, this is fine. So the next step here is n dp, or the new dp of j here. This one will be apre of r plus 1 minus, here in this case, apre of l, this one, plus mod mod, this one, modulo mod, the variable that we considered, or that we have assigned the constant modulo, or this one value. So this is fine. Let me come out of this one entirely. This one will be, let's assign the dp to the new dp, nothing but ndp here in this case, right? So we are moving to the current row, we are moving to the current row, means we are assigning the dp to the new dp here. So this is fine. Let me come out of this one entirely. Now we have come to the last part of the code. Nothing but here we have to sum up all the DP values at the top row. We have to sum up all the DP values at the top row, and we have to output the result. Initially, we will be going with the long here. We'll be going with the long because it might consist of the long this one value. I don't want to take the chances here by making use of the int, right? So if we don't have to make use of the big integer, at least we'll go with the long actually. So let me assign the answer to the value 0 or initialize answer to 0 initially. After this step, let's sum all the DP values at the top row. Here in this case, this will be for loop int. So j of this one, sorry, x position, where is x pos, this one, x position, this one of 0. This is fine. So let's assign answer to answer plus dp of j. This is fine, dp of j. Finally, mod modulo mod. This is fine. Mod is nothing but the constant mod value. It shouldn't exceed, right? 4 into 10 to the power of 6, I think. So this is fine. This one will be pw dot nothing but we are outputting the result. We are making use of the print writer. Pw is nothing but the print writer here. Pw, and we have to write the individual lines, right? Line by line. So we will be going with the println, and the variable that we have used here to the result, this one we are storing in the answer, right? So let's pass the answer here. So this will be answer. So this is it for the code. So this is it for the code, right? So we are done with the coding part here. We are done with the coding part. So let me have a sip of this one. So just give me a second here. So this is fine. So what we did here, yeah, we performed binary search. Then we have already discussed the approach, man. The only 3 steps, right? So the code is little bit lengthier because we are going with the input output as well. As we are solving the Codeforces problem, we are dealing with the input output as well. So the code is little bit lengthier. The first thing is only 3 things we have to note down here. First thing, what we need to do, from the bottom row to the top row, we have to store all the x values. We have to store all the x values that is present at certain positions, right? After doing that, we have to calculate the distance where this one, where the x is present at the last bottom row to the next bottom row, to the next row, means in the, suppose if you consider the example 1, we had 3 rows, right? 3 rows and 4 columns. So we have to calculate all the this one by making use of the Euclidean algorithm, whether it can be reachable by making use of Euclidean algorithm, whether we can reachable from the values that we considered from the bottom row to the next row. Nothing but row, from row 2 to row 1, row 0, row 1, and row 2 we had, row 2 to row 1. Next we have to do the same thing with the row 1 to row 0, row 1 to row 0, right? That calculation we have to do within for that one. For that purpose, here we will be making use of the DP. We will be making use of the we have made use of the DP and binary search in the middle. This is nothing but the optimization part. You can just do this one in the other ways as well. So this is meant to be solved with a DP. Basically, this is meant to be solved with a DP, and you can extremely optimize it by making use of the binary search. You can extremely optimize it by making use of the binary search. Constraints are very tight for this problem, right? Constraints are very tight for this problem. So you can just make use of the binary search, right? You can just make use of the binary search. And finally, after calculating all the this one, we have 2 conditions there. Either we can go solo, or individual value we can consider from the bottom row, or we can just consider 2 holds at a time. Means in the example 1, we considered from the valid path was after calculating the Euclidean distance and all. So we came to know that we can reach from 2, 1 to 1, 1, and from 1, 1 to this one 0, 1. This was one valid path, while we considered only one value, or while we went solo. Basically only 2, 1 we considered, and we can consider 2 holds at a time. When I say we can consider 2 holds at a time, we can consider 2, 1 and 2, 3 at a time, and then we can just move that one. We were able to reach by considering 2, 1 and 2, 3 to 1 comma 1, and then we were able to reach 1 comma 1 to 0 comma 1. This is also one possible this one other possible valid solution, valid path or the solution, right? So these were the two valid paths in the first example that we considered, right? So this is one thing, this is the second step. Mainly third step is we have to output the result or the value that we got, that is related to the input output, right? So this is fine. This is the simple thing that we need to keep in mind. So as the constraints are very tight, we are going with a DP, mainly binary search DP, along with the calculation of the this one prefix sum, along with the calculation of the prefix sum. So this is the main thing. So this is basically the approach that we went with, right? I hope the coding part is completely clear. Let's check whether this works for the test cases or not. So I hope this works. Let's see. So we have to get the output 260. We have three inputs right here. One is this one is this one, and this one. So this is fine. I hope this works, man. Let's see. So here we have the error where line number 8. So here new print writer I have considered. So this is fine. Yeah, new print writer of new buffered, this one here. So I didn't keep opening parenthesis here. I forgot, I think, maybe. Right, I forgot, I think, here. So let me close this one as well. So this is fine. Now if I run this, error has to go. Hey, what is the error now? 8 expected. Static print data pw new print data. New print writer. So this parenthesis is not required, opening and closing. So print writer of within that parenthesis itself, we are going with a new print writer. This is fine. Let me run now. So yeah, now we have cleared the line number 8, the error that was present in line number 8. So here what we have, error in the line number 14 in the input output. What error we have? Error not a statement. So we have given here so solution SO, and we have assigned this one to the solution, right? So what is wrong here? Solution, this is fine. Solution SO, this is also fine, and we are going with the new solution. Within the solution we are passing this one scanner as well as the print writer. What is wrong here then? Line number 14, while t this one greater than 0, this, oh, so this one I have to mention parenthesis here, right? So I forgot the parenthesis. So let me run this one again. So now we are left with one error. What is the error we are having? Line number 118. Let me come to 118. Hey, what happened here? When error class interface enum or record expected here. So here, let me do one thing. Just give me a second here. Just give me a second. So here, print writer dot ln. So I think I have given one extra this one bracket here. So let me remove this one because I copied the this one fast scanner, right? I didn't type this one. So I forgot to remove one this one bracket, I think. So here it has to be that bracket should be present here. Basically here there is only one this thing, what do you call, one this one bracket. So let me try now. Let me try running this one. So yeah, we have problem. We have a problem here. Line number 28, what we have now? Error, cannot find the symbol sc.nextInt. Cannot, variable nextInt. Location variable sc of type for scanner. Where is it? Line number 28 here. So here n equals sc.nextInt, comma m equals sc.nextInt. This is fine, right? What is wrong here? So yeah, nextInt. So yeah, here we have to give parenthesis, right? So here now we have, let's run this one. So now we have error in the line number 30. Error int cannot be dereferenced. So here line number 30, let me come to the line number 30. What is the error we are having here in this case? So within the solve, right? So let just give me a second here. What mistake I did now here on the line number 30. Alright, solve, this is fine. So this one line number 30. for int I equals 0, so this is fine. I plus plus, this is fine. Get of I or g of I equals sc dot. So this is not next int. We have to go to the next one, right? Not the int. Basically, we are just going with the next. So here this has to be sorry, not this one. Basically, this has to be next int itself. Line number 30. Oh, here also I have given next int. So this is not next int. This one has to be sc dot next, basically, right, to the char array. So this is fine. Now let me run this one. Um, so many errors, man. We are left with the 6 errors. What the heck? So here, this one, line number 32, incompatible types cannot infer types arguments for array list. So line number 32 here, what is wrong here? List of integer here, this one is fine. Array we have mentioned, x positions. So this one, new array list. Oh, here what mistake I have done, we have to pass the this one n, right? So we have considered n here. So this one has to be, we have to pass the value n within the array. So I have just given directly this one, angle brackets and parenthesis. Syntax, I've just went for the syntax, I think. So let me run this one again. So now we have cleared this one. Now what error we have? Unchecked conversion. This is warning or error? So this is warning is fine. Let's go with the line number 43. Error variable r is already defined in the method solve. Huh? So this one we are left with 5 errors still. So just give me a second here. The line number 43. Let me come to the line number 43 here. This one L equals lower bound I have given, R equals, so here where what error we are getting here now? Cannot find symbol, int L equals lower bound exposure. Cannot find symbol, variable R, symbol R. Huh? Cannot find symbol. So what error we are getting here? R where I have mentioned, L and R we have mentioned here, right? L and Kumar. What is wrong here? So here in the line number 42, I have made a mistake basically. So this has to be capital R. So that is the reason it is giving us the error. So here, what error it is giving? Variable R is already defined in the method. So this has to be capital R. So let's run this one again. So this error has to get vanished. Yeah, this is fine. Now we are left with the 3 errors basically. What error we have? Error variable R, again the same thing. Variable R is already defined in the method solve. So again we might have done the same mistake where it is line number 57 here again. So capital L we have made use of, this has to be capital R, man, not the smaller. Again this is fine. So let me run this one again. So here we are done with 2 errors. What is the error? Cannot find the symbol, cannot find the symbol prefix. So line number 58, let me come here. So we have sent this one here, right? So what is wrong here? So this is actually L and R I have given correctly. This is fine. Of j equals prefix of r plus 1 hyphen or minus prefix of L. Prefix of L, this is fine. R plus 1 minus prefix of L plus mod we are going with. So what is wrong here? Cannot find the symbol. Let's see what is wrong. First, let's do one thing. Let's concentrate on this error first. So we have here an error cannot find. So APRE R plus 1 minus it. So this has to be capital L, right? So we have to pass the capital L here. So I have written the code. I know this one. This is fine. L. Now this error has to get this one vanished. So yeah, we are done with one error and one warning. Warning is fine. What error we have here? I still am not understanding error. Cannot find symbol. So A of j, what symbol we are not able to find here? So let me go with here. A of j equals prefix of r plus 1 we have given. This is fine. It's fine in the line number 58, right? So this is fine. So minus prefix of L we have given. This is also fine within the array. Plus mod. So what is the mistake here then? So just give me a second here. So I still don't understand, man, what is wrong here. Prefix r plus 1. So this one, should we write this one in the array? Yeah, we have to mention this one in the array. Let's try this one. I hope this works. Let's see. So what we were having r plus 1, right? So r plus 1, I hope this works, man. Let's see. So yeah, we have the output 260. Thank God. Say, yeah, here actually I instead of the array I mentioned parenthesis here, so that is the reason it was giving error, right? And there were some typos. Basically there were some typos. This is fine. The code is little bit lengthier. This is fine, right? So now whatever the code that we have written works absolutely correct. We had to get the output 260. This is giving us some warning actually. So we can just go with the annotation at suppressed here. At suppressed warnings equals unchecked within the array. So this is fine. This works in, I hope this works in the this one, what do we call, Codeforces environment. Let's see. So this is fine. You can just ignore this warning for now. So the output that we got here is 260. That is what the output that we need to get here, right? So this is fine. Let me do one thing. Let me copy paste the this one signature starter template. Let me paste it over here, right? So this is fine. This is completely fine. And let me do one thing. Let me copy this one entirely and let me come here. So this one is the question F, right? So this one is F, basically Igor and the mountain, Igor or Igor and the mountain. So let me this one choose the F here and let me paste it over here. Let me paste it over here and let me hit the submit button. I hope this works, man. That warning, this thing, I'm concerned about the warning that I was getting. So I hope that doesn't cause any this thing within this Codeforces environment. So I hope this works. Let's see. Let's wait for some time on the test one. So this is fine. Why this is stuck? Yeah, you can see running on test 2. Yeah, let's wait for some time. So this is very slow actually running on test 3. Uh, Running on test 5. Let it run. Still this is running on test 16. Okay. So this is fine. No worries. Oh, this is very slow. one, test 42. Still, how many test cases are there, man? So yeah, you can clearly see here all the test cases got passed, right? So all the test cases got passed here, means the code got accepted here, right? So whatever the code that we have written works absolutely correct in this case. Whatever the code that we have written absolutely correct in this case. Again, I'm telling, so this is very simple. So basically, due to the high constraint, I mean strict or the tight constraints, we have to go for certain optimizations. That's it, basically, right? So first thing, what we had to do, so let's discuss the summary part very quickly. Let's discuss the summary part very quickly. Just give me a second here. So yeah, here first what we did, so we have to store the x, the value of x, position of the value of x, wherever it is found in the particular rows from bottom to top, right? From bottom to top, wherever the x is present. Then we have to calculate the distance, whether we can reach the distance from by considering the solo or by considering the two values, by considering one hold or by considering solo or by considering the two holds, means two positions at a time from the bottom row, right? So that one we can reach from particular row to particular row, or not, from the bottom row to next this one top row or not, right? So that one we will do. That is the next step, basically, by making use of the Euclidean, all this one Euclidean formula, right, to calculate the distance, and it has to be less than the small d that they have given in the input. In our case, in the first example, it was 1. So we ignored all the things that were the value basically which was above 1, right? So then we got the valid path, that is from 2 to 1 to 1 to 1, then from 1 to 1 to 0 to 1. So again, by considering the two holds at a time, so here this was for the solo value that we considered at the bottom row, then we can consider the two values at a time, two values at a time, or two holds at a time, in the bottom row. So we consider two holds at a time. That is also one possible valid distance solution, right? So we consider 2 comma 1 and 2 comma 3 at a time, and it was we were able to reach from there to 1 comma 1, and then from 1 comma 1 to 0 comma 1. So these were the two valid solutions that we got, basically, right? So this was the calculation part, and for this particular thing we made use of the DP and binary search. We made use of the TP and binary search for the optimization purposes, right? So we made use of the binary search and DP for the cache, DP for the caching, basically, right? So we made use of the binary search and the caching. Also, one thing, we went with the prefix sum calculation as well. We went with the prefix sum calculation as well, right? Just keep this in mind. Along with it, did we do something? No, right? Finally, we outputted the result, that is input output. So these are the steps that we need to remember for this particular problem. Else it is very easy. Else it is easy, not very easy, basically. This I wouldn't call very easy. This was a difficult question, this was a difficult question, but only thing is constraints are this one tight, and we have to go with the correct optimizations, right? So you can go with the other ways as well. This is the best approach that I found. This is the best approach I found. So this will be, we went step by step, we saw every step, right? So we saw every step, the same thing, whatever we discussed in the approach, we articulated in the form of code, right? We articulated in the form of code. I hope this question is completely clear, man. I hope this question is completely clear. I mean, I hope the solution part is completely clear, basically, right? Along with the approach and complexities, right? We have discussed the complexities already before writing the code. I hope the solution part is completely clear with the um, approach and complexities. For now, this is it. Thanks for watching, guys.